All right. Let's get started. So we're in the middle of going through set theory. We're going through it axiomatically. Unfortunately, the whiteboard got erased. So let's do a quick recap on the axioms that we already covered. First off, what was our first axiom of set theory? Axiom 1. Axiom 1 said that x's and y is a proposition if and only if x and y are sets. And so our example of how that was so useful is we considered the set of all sets that don't contain themselves. And was that a proposition, yes or no? Or we said, does a set of all sets, does it contain itself? And we asked, was that a proposition? And the answer is no, it's not a proposition. So the set of all sets that don't contain themselves turns out wasn't a set. We were trying to define a set into existence. Because this isn't a proposition. If we say let U equal all x such that x does not contain itself, so U is equal to the set of all sets that don't contain themselves, then does U contain itself? Well, if it does contain itself, and U is a set of all sets that don't contain themselves, then it doesn't contain itself. But if it doesn't contain itself, then it does contain itself. And so the problem was we were just calling U a set, as though we were somehow justified in thinking this was a set. It was kind of like me saying, consider the prime number 6. 6 isn't a prime number. Just because you call it one doesn't make it so. So I said, consider the set of all sets that don't contain themselves. Just because I call it a set doesn't magically make it a set. And so we're only justified in calling it a set if this is a proposition. So this is a proposition if and only if x and y are sets. So that was our first axiom, and it gave us our primitives in this axiom as well. Our two undefined terms are that is a member of a relationship, and then set. That's our other undefined term. And so in all of set theory, those are our only two undefined terms, set and is a member of. We also have this notation. So I guess we can call that a primitive if we want as well. So that set and then that type of notation are the types of things we don't define. So that was axiom 1. Axiom 2 now is a pretty simple one. Remember what axiom 2 was? Axiom 2 is the axiom that says there's an empty set. And we proved that there was one and only one empty set. So axiom 2 guaranteed us there's at least one empty set. We proved that there's one and only one empty set. And therefore, since it's unique, we can define it. And so we use that symbol to define it. So we defined a new term in our axiom. It turns out, well, I should say that. But so there we go. We have a new term defined. That's what axiom 2 gave us. Axiom 3, if I'm remembering these in the right order, axiom 3 is one that says if x is a set and y is a set, then this is a set, where its members are the sets x and y, and that's it. Its members are precisely x and y. So if x is a set and y is a set, I know that there must be some other set containing exactly x and y, and this is our notation designating that set. I think that was axiom 3. Let me double check these as I go. Yes. Axiom 4 was our union axiom. So axiom 4 says that if I have, don't want to accidentally say this word, because we use that union notation a little bit different. So I have a concise way of writing it down. Here's the precise language, so I don't accidentally make a mistake, and then we'll get high-level intuition of this again. For all x, there exists an m such that for all y, if y is in M, then that implied that there existed a, what did I use last time? An S, such that S is in X and Y is in S. Sorry, writing real small there. And then finish square bracket. Okay, what does this say? Let's write out a concrete example really quick, and then I think I'll make it more clear. So I have X is equal to the set containing the set 1, 2, comma, and the set 3, 4. So there's X. So for any set X, here's an example. And it turns out that this is going to apply to sets that are sets of sets. That's what it's going to be useful for. It's our union one. You can union those together. It's saying if you can write a set X like this, then there must be some set out there called M equal to the elements of X. So 1, 2, 3, 4, like that. So in our example up here, one of these inside sets right here is what we mean by this S. And what we mean by one of these particular elements, like the 4 here or the 4 here, is what we mean by Y up here. So for all X, there exists some M such that for any Y, anything you pick, if that thing is in M, then there must have been a set S in X where Y was also in that set S. Does that one make sense? It's one of those ones that you kind of just have to stare at a bit until you see it. For every set, let me say, make this match up a little bit better. Here's an example of an S. Okay, so for any set X you choose, there must exist some set M such that the elements of M are the members, are the elements of X. That's a high-level way of saying it. Now let's go through this again. For any X you choose, here's an X I chose, there must exist some M, here's my M, such that for any Y you choose in M, pick any one of those you want, we'll pick 4. There must exist some set in X, call it S, such that there must exist some set S in X where Y is also in S. If it's in here, then there must have been some set in X containing it. And in that case, we use this notation and we say M is equal to the union of X.
This axiom is what makes it possible.
This axiom is what enables us to union sets together. Because from axiom 3, I already know if you have 2 sets, I can stick them inside some set. Now axiom 4 says, now you can take those 2 sets and you can union them together. Now we could have also unioned 3 sets together and 4 sets together and 5 sets together. Didn't have to be 2.
I get that it says you can. And in our previous class, you said that they were equal.
No. This is not equal to this. Very different.
I was confused because you couldn't.
That was a complete mistake. What I meant was this. The union on X is equal to M, not X is equal to M. I can't believe I did that. Okay, that's awful. Yes, this is what's true. This set and this set are very different things. Speaking from a high level, how many elements are in X? 2. How many elements are in M? 4. So they're very different sets. They're not even the same size. Cool. All right, so that was axiom 4. That was the union axiom. And just for the sake of one more example, let's look at the union on the set containing the set 1, 2, comma, the set 2, 3, comma, and the set 3, 4. What's that equal to? The set containing 1, 2, 3, 4. So I did 2 by way of example just because it was simpler, but we can union up any collection of sets. Okay, so the union of this set is what gives us that. Now, sometimes it's nice to cover the exact same thing twice for everything up. Okay, so now that we did the review of those, we get to Axiom 5, which is where we basically have to just give you all this jargon to give you Axiom 5, all for the sake of set builder notation. So what we're after is set builder notation. So here's high level what I want to be able to do. Let's say M is equal to the set 1, 2, 3, 4, 5, 6, 7, 8. And what I want is a way to talk about all the even members of M. Now this is kind of a small set, but if I wrote a massive set down and I want to write out, okay, now what's all its even members, it'd be very tedious to have to manually write all its even members. I want some easy way of just extracting all those even members. So I define some predicate, P of X, and P of X is the X is even predicate. Or, for those of you who have had some discrete math, we define P of X to be logically equivalent to 2 divides X. There's a more precise way of doing it, but for the sake of high-level intuition, stick with this. So P is a X is even predicate. So then I want to be able to just talk about all its even members by just saying, so the evens, we'll call it E. E we want to be the set of all the X in M such that P of X is true, or in other words, X is even. And we want this to be shorthand, in this case, for the set 2, 4, 6, 8. So this is set builder notation. From some existing set, we want to apply some filter, some predicate that spits out true or false. If it spits out true, it means it ends up in the set. If it spits out false, it means it doesn't end up in the set. 1, we plug that in. 1, true. 1 is even, false, so we don't include 1. 2, when we plug it in there, it's true, so we include it. So this is some condition. Every time it comes out true, we include the member. Every time it comes out false, we don't include the member. So we're trying to set up so that we can use this set builder notation, and we have to justify that this is actually a set. We got to make sure that we're not accidentally doing this. Let's take the set of all sets that don't contain themselves. We have to be very sure that we're talking about a set. So we're about to do a lot of work to justify, hey, when we do this, it's a set. We're good. So let's nosedive into that work. Okay. Sorry, some of this was from last time, and some of it I added. So I added starting at this blue line. So we're going to go here, here, and then go back to start the whiteboard. I just rewrote the stuff that was over there that got erased. Okay. So let's start with a functional relation. Let's even remember what a relation is. What's a relation? Maybe let's start with predicate. What's a predicate? A Boolean valued function or a proposition valued function. You give it something and it spits out true or false. We just wrote one. The is even predicate I just erased. It's a predicate. You give it something and it spits out true if it's even, it spits out false if it's not. Okay, so now that's a predicate. What's a relation?
Relation is when you have two parts of the predicate. It's not a predicate with a lot of values.
Yeah, a relation is a predicate that takes 2 terms. That's it. So loves is a relation. If you think about on the set of people, X loves Y. true or false. Give me two people, and you can always spit out true or false. Common relation on the numbers, the less than symbol. Less than. Usually we write x less than y so that we know where the terms go. That's a relation. Takes two terms and spits out true or false. So a relation is functional. A relation R is functional if and only if for every x there exists one and only one y such that x is related to y. Let's give you an example of a functional relation. We'll say that x is related to y if and only if. So we'll define this relation to mean that y is equal to 2x. That's what we'll define it to mean. X is related to y if and only if y is double x. So now let's plug 2 into this. Obviously, this is a relation on numbers. So let's plug 2 into this. So what would 2 be related to under this? 4. 4 is the only number it's related to. There is no other number it's related to. So for any number you choose, for any x you choose, for all x, I can always find a y, and there's one and only one y I can find that would satisfy the relationship. For any x you choose, there's one and only one y I can pick that satisfies this relationship. And obviously, it's the one that's double what you choose. This tells me exactly which one to choose. If you choose 2, I just multiply it by 2. If you choose pi, I choose 2 pi.
Can we get an example of relations?
Sure. I don't know what symbol you want me to use. We'll use the relation S. X, S, Y. We'll define that to be X is related to Y using this relation S if and only if X is less than Y. I can plug for, if you pick 2 now, what Y can I choose? I can choose 3, I can choose 4, I can choose 5, I can choose 6. So this is not a functional one. It's a relation, but it's not a functional relation. This is a functional relation. For each x, there's one and only one y it's related to. Make sense, the difference there? Okay, so that's what this definition is, a functional relation. Okay. Maybe we'll keep this one up here because we'll be talking about an example of this. Now let M be a set and let R be a functional relation. So we'll keep this our functional relation. Let's pick some set M to make this definition make sense. So M, we'll make it the numbers, I don't know, 1/2, 2, and 7. Doesn't matter what it is. So I've got, let M be a set. Okay, there's some set. And R be a functional relation. Then the image of R on M, the image of R when we plug in M, consists of all those y's for which there was an x in M such that x was related to y. In other words, the image of R on M is all the y's we would get related to these if we plug these in as x's. So if I plugged in 1/2, what's 1/2 related to? Huh? 1. When you double 1/2, you get 1. What's 2 related to? 4. And what's 7 related to? 14. Now, we use this notation with functional relations that everyone just gets used to. And what we really write is R of 1/2 is equal to 2. R of 2 is equal to 4. And R of 7 is equal to 14. So this is another way we commonly write it with functional relations. And that's the way we read it. R of 1/2 is 2. And another way you would have seen this defined, rather than saying x is related to y if and only if y is equal to 2x, you would have just seen it R of x is equal to 2x. Did I write something different? Thank you. I was probably thinking to plug 2 in next. So that's notation for functional relations. You'll get used to that. That's the way everyone writes functions.
So can you talk a little bit about the usefulness of defining relations this way compared to discrete math? We defined it as a set of ordered pairs. Because they're really, I mean, they capture the same kind of thing, but a set of ordered pairs seems so much simpler than not necessarily a functional relation, but a relation.
Because, so the way we defined a relation in set theory, it's kind of using the naive set theoretical way of doing, well, I shouldn't say that. A relation is a much, okay. In discrete math, we're already using set theory to define relations. And we would call that a set theoretical relation. But a relation is a much more broad concept than just what set theory gives. Because a relation is a logical concept. It's still a valid concept in logic. And so here's what we mean. Here's relations. Here's set theoretical relations. And every set theoretical relation is still a relation. And so we can use it just like we use all other relations. But since it's a more restricted notion, it also gives us more we can do with it. Because we know that set theoretical relations have other nice properties. So it's just going to be a more restricted notion. But you can't use a set theoretical relation in logic. Because you have to use logic to construct set theory. But we will eventually get to that notion of a relation. Just a set of ordered pairs.
Well, it seems like we'll probably get to that.
I imagine maybe next time, yeah. And we'll also talk about a function as a special type of relation again. And it's going to turn out to be the same thing. You've got a relation, a function's a special type of relation, blah, blah, blah. And it turns out it'll be logically equivalent with a functional relation like we have defined here. Anyways. Okay, so there's a functional relation. Oh, we just did this one. So let M be a set and R be a functional relation. Then the image of R on M consists of all those Y's for which there was some X in M such that X was related to Y. So before, sorry, I erased it too soon. We said X was related to Y if and only if Y was equal to 2X. We said M was equal to 1/2 to 7. And so all our Y's turned out to be, so the image of R on M turned out to be 1, 4, 14. These were all the Y's we got out. So let M be a set and R be a functional relation. There they are. Then the image of R on M, consists of all those Y's for which there was some X in M such that X was related to Y. And then Axiom 5 says, and this image, I drew it as a set, but we didn't know it was a set. Axiom 5 says it is a set. That's all Axiom 5 says. So if relation R is functional and M is a set, then the image of R on M is also a set.
Like a simpler way to recommend code last time.
My role a little bit different. Just get the idea in my head, then write it down. Not write it word for word because that's hard.
I understand like term image, range, yeah. In this context, though, it's a little confusing. R.
The image of R on M.
Yeah, what do you mean?
So you're used to a picture something like this. Here's X, here's Y, and F is a function that maps each of these to these. And you call these over here your domain, and you call these over here your range. In our picture, this X over here is acting the exact same way as M. This is the image of M on F. So rename f r. Now y is equal to the image of r on m. Y over here, your range is the image.
Why can't you just, so to plug in a set R, you have to say the image of it, which is essentially all the different outputs.
Take all the outputs and collect them up. It's the range. The image and the range, identical. No difference.
Okay, if you were not to have the image plugged into the set, would it be basically like a single value, output a single value?
So we can talk about the image of the whole domain, or we can talk about the image of one element out of the domain.
So to the term image, you're referring to that you're plugging each and every single one of the elements in and getting an output.
So I would say, so if R is defined this way, I would say the image of R on 2 is 4.
Right.
And I would say the image of R on 1, 2 is 2, 4.
But would you have to put the term image on the side of it? Yes.
You're saying like that?
Yep.
Yes.
Because otherwise you're
When we're
plugging
doing
in
sets.
the set, not the elements.
Correct.
Okay.
But that is going to be a little bit confusing terminology, because sometimes we use image to refer to the output of a particular element, and then sometimes we use image to refer to what all the elements map to. So sometimes it's a set, and sometimes it's a particular output.
Just omit the image.
We would omit it here. I'm saying in terminology.
Oh.
So it can be a little bit confusing, and usually I'll try to make it clear from context. But you're right in this case. When you see image of R on a set, that tells you, hey, we're going to have a set here.
Yeah, plugging in each one of it.
Yeah, and collecting them together in a set. Right. Okay. Axiom. Okay, we did Axiom 5. Okay, now our theorem. Our theorem, which is a big kick in the teeth for your intro to set theory. So let P of X be a predicate. Any predicate doesn't matter. Let P of X be a predicate and let M be a set. Now remember what we're going to try and define here. We're going to try and define what it means to take all the Y out of M that satisfy that predicate. I've got M, and I want to use some predicate to filter out the elements and collect all the elements I care about. By taking a set and pulling out all the even numbers. One thing we might do. So that's what we're trying to define. We're trying to define this notation. So let P of X be a predicate and M be a set. Then all the Y in M, such that Y satisfies P, or in other words, P of Y is true, denoted this way, is a set. And we're going to prove that. We're going to prove that all the Y in M, such that Y satisfies P, or in other words, P of Y is true, and we denote it this way, we're going to prove that it is a set. How are we going to prove that it's a set? I'm going to come up with some functional relation where all these Y's that we care about, all the Y's that end up in here, are the image of my functional relation. I'm going to make the image of my functional relation this exact set. I'm going to make the image of my functional relation all the Y in M that satisfy P. And then Axiom 5 tells me it must be a set. All right. So let's go over this again. So let P of X be any predicate, and let M be any set. We have one of two cases. Maybe draw a random picture over here. M we'll say is a set 1, 2, 3, 4, 5, 6. And we'll say P of X is even. Say X is even.
This assumes that the set we're dealing with is part of the domain.
Yeah, M is what we're plugging in to our predicate. I'm taking M and I'm filtering it by this predicate. Okay, so one of two things happens. So let P of X be any predicate and let M be any set. Now one of two things happens. Either there is something in here that satisfies this, or there's nothing in here that satisfies this. One of those two things has to be the case. Either nothing in here is even or something in here is even. Now, if nothing in here were even, then the set of all the things in here, let's pretend P of x was something else. Let's call this P prime of x for a second example. Is the x is greater than 6. Okay. So if this were a predicate, then nothing in here would satisfy it, right? And so then the set of all y in M such that P prime of y, what are all the y in M such that y is greater than 6? There's nothing. So remember, we're defining this notation right now to be a set. In that case, we're going to define this to be the empty set. That's what it's going to be. So that's our first case. If there does not exist a z in M such that z satisfies the predicate, such that P of z is true, we define this set to be the empty set. And so this notation is a set. That's what we're proving. This notation always gives us a set. All right, so that's the first case. Now the second case is when we're dealing with a predicate like this one, where there is something in there. If there does exist a z in M such that P of z is true, if there does exist something in there that satisfies the predicate, we're going to define the following functional relation on M. And this is what our relation is going to be. Big ugly thing, but we'll get used to it here. So we're in the second case where there is something in here that satisfies it. We need to call one of those things z. So I'm guaranteed that there is some z in here that satisfies the relation. And we're going to call it z. So what should we say z is in this example? 2. 2 is something in here that satisfies it. So we'll say z is 2. So if there exists a z such that P of z is true, define the following relation using z. So we picked our z in there. Now we're going to define this relation. And our relation is x is related to y if and only if x satisfies P and y is the same thing as x, or x doesn't satisfy P and y is the same thing as z. Or in our concrete example, what is this going to say? X is related to y if and only if x is even and y is equal to x, so y ends up even, or x is not even and y is equal to z, which is 2, so y is still even. We're setting this up so our y's are always even numbers out of n. If x is even, y is the same thing as x, so y is even. If x is not even, then y is the same thing as z, which is even. And so then x is related to y. So if x is related to y and P of x is true, or in other words, x is even, then y is equal to x, and so y is a member of M where y makes a statement true. If x is related to y and P of x is false, or in other words, x is not even, then y is equal to z, and so y is a member of M where P of y is true. So in either case, y is going to be a member of M that satisfies P, no matter what. Let's write it out very concretely for this example here. What's everything related to? Let's write out all our x's and all our y's. So all our x's always have to be members of M, and we'll see what our y's are. So in the case where x is 1, what's 1 related to? Looking at this. What is a y that could possibly satisfy it? So x is related to y if and only if one of these two things are satisfied. This has to be satisfied or this has to be satisfied for x to be related to it. So let's see. Remember, x is 1 in our example. Is 1 even? No. So there's no way to make this part true. So we have to make this part true with our choice of y. Is x odd? Yeah, or is x not even, I should say. Is x not even? Yes. Then the only way we can satisfy it if y is the same thing as z. And in our concrete example, z2. So our y has to be 2. Using this relation right here, 2 is the one and only thing that 1 can be related to. If your x is 1, your y has to be the same thing as z, which in our case is 2. So 1's related to 2. What's 2 related to? 2 is related to itself. 2 is even. 2 satisfies it. And so the only way to make this whole thing here true is if y is the same thing as x. So 2 is related to 2. So if your x is 2, y has to be 2. That's the only thing that satisfies the relation. If you picked any other value of y, it wouldn't satisfy the relation. What is 3 related to? Let's see. Is 3 even? No. So now we have to satisfy this side. Is 3 not even? Yes. So y has to be z, which is 2. Let's say z equal to 2 up here, so I have root to right. Okay, what's 4 related to? Itself. 4 is even, so y has to be the same thing as x. 4 is related to itself. 5, it's not even, so it's related to 2. 6, it is even, so it's related to itself. 7, oh, we didn't have a 7. So notice, all the things that satisfied the relation, we just paired with themselves. All the things that didn't satisfy the relation, we just paired with an arbitrary thing that did satisfy the relation. In this case, it was 2. But it wouldn't matter if I paired all those with 4. It wouldn't matter if I paired all those with 6. I just paired them with something that satisfied. Now look at the set of all our right-hand elements. Let's look at the set of all our right-hand elements. There's 2. There's 2 again, but duplicates don't matter. There's 2 again, but duplicates don't matter. There's 4. There's 6. So a set of all our right-hand elements is exactly 2, 4, 6. And we're guaranteed that all our right-hand elements are a set from axiom 5. So this, in this case, this is what we would mean. This is the set of all y in M such that d of y. Or in other words, this is a set of all the things in here that are even. It's P4, 6. A lot of work just to define the set builder notation. Any questions on that? After seeing it 2 times, kind of clicking? Okay. So then for all y in M such that P of y, we define it to be the image of R under M, which is a set. Okay, axiom 6. Axiom 6 is our axiom for the power set. In short, it says the power set exists. Now let's go back to naive set theory first and think about how we would define the power set. We would say that the power set on some set M, we would just define that to be the set of all x such that x is a subset of M. That would be naive set theory. The set of all possible subsets of M. Let's get a concrete example real quick and then go back to thinking about this. So what's the power set on the set AB? This is equal to the set of all the possible subsets of AB. What's a possible subset of AB? The set containing AB is a subset of AB. So here's one subset of AB, the set AB itself. Okay, there's one. What else is there? The set containing just A, not A by itself, but the set containing A is a subset. The set containing B, and that's all of them, right? Oh, the empty set. Good. Okay, so there's a set of all possible subsets of AB. That's what we mean by the power set. Now here's a naive set theory way of defining power set. Just take all the x, such that x is a subset of M, put them in a set together. There you go. What's wrong with that? We can't use this kind of set builder notation. We have to say the set of all something from a set. So if I want to use our set builder notation, I would have to say the set of all x in something such that x is a subset of M. And what would that something be? I need some bigger set I'm pulling all those subsets from. And so I'd have to be able to somehow define that first. before I could use our proper set builder notation to define it. And so that's why we have to introduce it as an axiom, that such a set does exist. Because there's no way to define it with what we already have. There's no way to get that bigger set from which we pull out all the subsets. Does that make sense? So that's what axiom 6 says. Let M be a set, then there exists a set P of M whose elements are precisely the subsets of M. So if M were the set AB, then that fancy P of AB would be exactly what we have there. And what?
I mean, everybody tried without capturing the idea of words.
Let's think about it for a second. We would say something like X in PM logically equivalent to X is a subset of M. I don't know, something like that. So P of M is a unique set such that this is satisfied.
For all X to exist.
For all M,
For all M.
there exists P of M such that if X is a subset of M, then X is in P of M.
X is a variable.
Is it a free variable? It's a free variable because it's showing up on both sides of my expression, which is okay. You just can't have a free variable show up over here that wasn't a free variable over here.
Right.
So there's no way for us to construct this power set with our given axioms, and so we have to introduce it as an axiom that for any set, its power set exists. That's just assumption. One of our axioms, no way for us to prove it, no way for us to derive it. Now, it's very common from here on out for people to just define the power set this way because it gives you the intuition for what it means. But strictly speaking, the power set doesn't have a definition. But this gives you the intuition. The set of all y such that y is a subset of n. So naive set theory, super useful for giving us good intuition, although strictly speaking, if you try to use this all the time, you might get yourself in trouble and start defining sets into existence. Yeah, like the set of all sets that don't contain themselves. So you have to be careful with the set builder notation. Set builder notation like we defined, where it's always y from all sets such that some condition about y, that's always, you're in the clear there. You're always good there. But this set builder notation, where we didn't say this y had to come from some previous set, it's possible you get yourself in trouble. And so you could accidentally not be talking about set. It took people a long time to figure out that the set of all sets that don't contain themselves was in fact not a set.
So in this case, I don't know how that represented the set of all sets don't contain themselves. What is y and what is not?
So we did that. What we did before is u is equal to the set of all x such that x is not in x. It turns out that doesn't work. because it makes like this is not a proposition. Is that true or false? Well, if it's true, it's false, and if it's false, it's true.
Right. So how do you connect that to the other definition?
Well, notice that this is using the same naive set builder notation. It's just saying the set of all y satisfying some condition.
You'd say,
If we were being more careful, so using our careful set builder notation, then we would have to say the set of all x in some other set such that x is not in x. And now we have to make sure that all these x's that we're talking about are in fact sets. Because they had to come from some other set here if we use a set builder notation. So the set builder notation we use is always taking sets and restricting them in some sense. And so we are guaranteed to have a set because the thing that we start with had to be a set. Here, we have no clue where those x's are coming from.
right.
So this can get us into trouble, but it's super useful to use it sometimes. This will never get us into trouble, but it can sometimes be tedious coming up with that set.
I was just wondering if there's an intuitive way to understand. If your power set is the set, I know it doesn't exist because there's no set that is all the sets don't. But if you were trying to define P of n to be a set of all sets that don't contain themselves, what would n intuitively be?
P of m.
If P of m was the set of all sets that don't contain themselves, and you were trying to represent it with this notation.
Here's how I would represent with naive set builder notation.
Right, so what would n be?
M is just a set.
Any set?
Any set. And so we're just saying take the set of all things that are its subsets. And if we were to write this out precisely, then you'd see it has kind of a stupid definition. Because then we would say, if we write it out precisely, we say P of m is equal to the set of, for all y in P of m, where y is a subset of m. And now that's stupid. That's how we'd write out precisely.
Which is weird because you're
Right.
some
And
definition.
right.
Okay, so the axiom is present circular definition.
Exactly. There's no other way to define it, and so we have to introduce an axiom. But in naive set theory, that's how it's defined, and also gives you great intuition. If we were in discrete math, I would have given you this intuition, we would have gone on our merry way. Because it's pretty close. It gives you the right idea.
I think axioms are just cop out.
They're not.
Because we say, oh, they have no definition. Well, clearly they are defined.
Axioms are what are dictating the field that you're in. Let me give you a great example of when we first discovered that there were different fields. It was a switch from there being just Euclidean geometry to the discovery of hyperbolic and Riemannian geometries, or elliptical geometries. So here's one of the axioms in Euclidean geometry. Given a line and a point not on the line, then there exists one and only one line through the given point, such that the two lines never intersect. Is that true?
Yes. I don't know.
There's only one line. Remember, a line goes on forever. There's only one line I can draw through this point. One line I can draw through this point such that these two lines never intersect. If I tried to draw a slightly different line, it's eventually going to intersect. That's an axiom for Euclidean geometry. If we're in what we call elliptical geometry, there are no two lines you can draw that don't intersect. An example of elliptical geometry is the surface of a sphere. And the logical equivalent of a line in elliptical geometry would be a great circle on the Earth. Something that goes around the diameter of the whole sphere. So pick any line that goes all the way around the sphere, and pick any other line that goes all the way around the sphere, and they're always going to intersect in two places. And so if your axiom says that there's only one line, such that they don't intersect, then you're in Euclidean geometry. If your axiom says there are no lines I can draw through the given point such that they don't intersect, then you're in a elliptical geometry of some sort. On the other hand, if we had, I don't really have anything in here to model this like a saddle of a horse. So you think about a horse's saddle, except for as it spreads out, extend it into infinity. Now, through any line and through any point, I can draw an infinite number of lines, such that they never intersect, and we call that hyperbolic geometry. So which of those axioms you choose is putting you in a different field of mathematics. Are we talking about Euclidean geometry? Are we talking about some sort of elliptical geometry? Or are we talking about hyperbolic geometry? The axiom is what's telling us which of those fields we're in. And so a particular set of axioms gives you a particular field of mathematics. So what you're calling a cop-out is really scoping you to talking about one thing. I can't talk about every field of mathematics simultaneously. Not every field of mathematics is the same. Euclidean geometry is very different from elliptical geometry. Simple example, if I draw a triangle on the surface of the Earth and you add up its angles, it's always going to be more than 180 degrees. On a flat board, you add it up, it'll always be exactly 180 degrees. On a hyperbolic surface, it will always be less than 180 degrees. So things come out differently, depending on what kind of geometry we're talking about. So axioms are what dictate the field that you're in, the logic set. And we have fields where we know we want certain things, and if we can't construct it from what we already have, we need an axiom to give us that thing. So we know that when we're talking about sets, we want to be able to talk about the set of all its subsets. That's a very useful thing to talk about. Question is, can I construct it from what we have? No. So then I need an axiom that introduces it. Anyways, we have a tangent there. I already did this example. The set of all subsets of AB. Remind ourselves of it one more time. The power set of AB, that's the set containing, we have the empty set, the set containing A, the set containing B, and the set containing AB. And I put 3 elements in there, but then I have to write out 4 sets, or 8 sets, and I don't want to do that, because it blows up fast. If you talk about the power set of a 10-element set, how many subsets does a 10-element set have? Those of you who 2 to the power 10, which is 1024. So these can quickly blow up. All right. Another definition. The cross product of 2 sets. If I take the set X and I cross it with the set Y, what does that give me? Let's look at the naive version of it first. X cross Y, that's a set of all order pairs AB, where A is an element of X and B is an element of Y. Here's the way I define it for you if we were in a naive set theory class. Here's its proper definition. I need to specify where the order pairs AB come from. And they come from the power set of the union of X and Y. Now that is just atrocious. And so while it's great to have precise definitions, it can also be a bit tedious to use them. And so this gives you an example of how naive set theory is absurdly useful and why it's so frequently used. So we use strict set theory to make sure we're not accidentally doing something against the rules. And after that, we use naive set theory because it's much more concise. So this will be the only time that you'll ever see this terrible definition. Here's what you'd see in every other math class.
Can you explain why that?
I am not going to try and make this set appeal to your intuition in any way, shape, or form. If you would like, you can pick a small set for X, a small set for Y, because even if you pick a 2-element set and a 2-element set, union them together, that's a 4-element set. Now take their power set, that's a 16-element set. The power set of a 16-element set, you're in trouble. So, this blows up very fast.
Is this like a way to say basically any possible, I don't understand the power,
The fact that this gives us ordered pairs, there's no reason for that to appeal to your intuition. But remember that an ordered pair has a precise definition. Remember that the ordered pair AB is set theoretical definition was a set A, comma, AB. And so if you were to expand that thing out, you notice that it had things like this in it. And it's going to have much more than just those ordered pairs, but it will have all those ordered pairs. And so you can pull them out of there. Geez Louise is right. So we want to make sure that we're not talking nonsense. But once we're guaranteed we're not talking nonsense, we want to drop the horrendous notation and just use the clear notation. So going forward in topology, we're going to drop horrendous notation and just use this precise notation. So we've seen how the precise notation can get you in trouble, but we also see how it's very nice to use it instead. Or not the, I think I said that wrong. We see how the naive notation can get us into trouble, but we also see how it's much nicer to use in a lot of cases. And so we're going to be being fast and loose and using naive set theory rather than properly defining everything. Okay. Now let's just write out some set operations here with some examples just to make sure we're all on the same page. Make sure that's not rubbing against my pants. That'd be annoying. Okay, so here's a set A, B, and C. Let's really quick write out some other things. So what's the union on the set containing A, B, and C? That would be the set containing 1, 2, 3, 4, 5. Remember, it's in the union if there's some set containing that element. It's the elements of the elements of this set. What about the intersection of A, B, and C? Just a set containing 3. We defined it last time. You use union to define intersection. Okay, let's see. Cross product. Well, let's also use the infix notation to make sure we're good with that. Well, if you just saw a union be like this, what does that mean? That's just 1, 2, 3, 4. So A union B just means apply union to the sets A, B. Same thing. Oftentimes we're just unioning a couple sets together, so this is very common infix notation. So this and this give us the exact same thing, which would be just a set containing 1, 2, 3, and 4. Similarly, what's A intersect B? Just a set containing 3. And that's identical to the intersection of A, B, like that. Same thing. Okay, cross product. Let's cross one with the 2. So let's look at what would B cross A equal. Yeah, what's something that would be in here? 3, 1. So the ordered pair 3, 1 is in here. Oops. 3, 1's in there. 3, 2, 3, 3, 4, 1, 4, 2. Sorry, let's parentheses. 4, 2, and 4, 3. Now notice that B cross A is very different from A cross B. What would A cross B be? Flip the order. So that would be 1, 3, ... Flipping the order of each element as we write it. So those are 2 very different sets. B cross A is not the same thing as A cross B. Notice A union B is equal to B union A. That's the same. And A intersect B is equal to the same thing as B intersect A. That's the same. So union and intersection, those are commutative. Cross product is not commutative. Oh, and we also did a minus last time. See if you remember this. Pretty intuitive, though. what would A minus B be equal to? It's everything in A that's not in B. So in this case, it's just 1, 2. And what would B minus A equal? It's everything in B that's not in A. So in this case, it's just 4. So again, minus is not commutative in set theory. Good with those?
Is there a notion for like three-element cross product, cross A, cross C?
Yes.
But that'll have to have nested.
It's ordered triples,
Yeah.
but an ordered triple is just a nested ordered pair. That's what it is by definition.
They just decided to eliminate that set of
By definition, A, B, C, I can't remember which way it goes. This is defined to be, I think it's this way, A, B, C. Where we already know that's a set and we already know that's a set. And so then it's just recursive from there. Yeah. So then, yeah, you can use that notation. And it works for any n element list. It's just order couples inside of order couples inside of order couples. 2 element sets inside 2 element sets inside 2 element sets inside 2 element sets. Okay. So I think that covered all the basic set relations and operations.
Out of curiosity, you can, so you have a union symbol and then you have a set of sets, all those sets, and you want. With that notation, you're really only two sets at a time.
Kind of. It's the same way that you have this.
Okay.
Strictly speaking, you have to have parentheses, and so we'd have to write it like this, or something. And so we plus those together, which gives us a number. Then we have a number plus a number, so it's always doing 2 at a
So
time.
you're always doing 2 at a time, starting left to right.
Left to right is completely arbitrary
And
here.
that applies to all. So all symbols have the ability to do that. The minus symbol, the time symbol, they all kind of, if you were to set that symbol and then add
It has to be associative. It means it doesn't matter where the parentheses go.
Oh, yes, it does.
No. If I were to change the parentheses so that we instead add those together first, and then we add those, and then we add those. Right.
Okay.
So that's what we mean by associative. So as long as it's associative, then putting a bunch of them in order like that doesn't change anything. But if you're worried about it, you can always add parentheses to be very precise. And so, yeah, it may be the case that you say, let's look at X union together with Y union together with Z. Really, we should prove that union is associative before we go around doing things like that. But once we prove it's associative, then we're okay using this notation.
So is there, I know we use the order operations in cases where it's not associative, but do we ever define that anywhere for developing a particular analysis?
Define the order of operations. A bunch of it comes from our logic precedents.
Yeah.
So there's just an understood precedence in logic, and we just have to say it. This is our precedence, so we don't have to put parentheses everywhere. And the precedence was given as not, and then or, and then implies, and then logical equivalent. And that's just stated, and it's just understood. And then from there on out, all these other things are giving meaning in terms of these things. And so, for example, now we're going to go to naive set theory way of defining union. What do we mean by A union B? And you see why it's absurdly useful. We define that to be the set of all X such that X is in A or X is in B. And we define A intersect B to be the set of all x such that x is in A and x is in B. And so then your intersection operator ends up having the same precedence as and your union operator ends up having the same precedence as or.
We don't really attempt to define addition and subtraction.
You're saying addition and subtraction as though we were to construct arithmetic?
Yeah.
They have their definitions.
And it preserves precedence.
So our precedence is given to us. Let me think about this. Don't want to accidentally say this right or wrong. I want to say we get it from the distributive.
So is the precedence, is that all contained in the build axioms?
Think. I want to say distribution tells us that we have to do our multiplication before our addition, and then division is defined the same way as multiplication, so it doesn't matter the order on those. And then subtraction is defined using addition, so it doesn't matter the order on those.
But order does matter.
No, you just write it bad. It doesn't matter if you do your subtraction before your addition, if you write it right.
But 6 minus 8.
No, we're talking about precedence.
Yeah,
So
precedence, not
if I do 9 plus 3 minus 7, doesn't matter if I do the 3 minus 7 first,
I can't remember. Prove that addition.
and then do 9 plus it, or did we prove? No,
Or was that an axiom?
it's an axiom. Commutativity and associativity of addition and multiplication were axioms.
Gotcha. But not division.
Division and subtraction are defined.
Right.
Yep. And then they inherit their associativity and commutativity from multiplication and addition. Yep. Okay. So we did the set notations, basic set notations that we're going to see. So now we're ready for Axiom 7. Okay. Axiom 7 is our axiom that gives us infinity, or our axiom that gives us the natural numbers. Now I'm going to give you an old version of Axiom 7 and then the one that we pretty much use today. And then we'll stress this one more than this one. I'm going to rewrite it twice.
Why do both?
I mean, maybe you guys don't care, just because it's one that comes up a lot. The very common version of it, and then the more modern version of it. So the very common version of it, there exists a set that contains the empty set, and for every set y it contains, it also contains the set containing y. And you notice that, those of you who used to proof by induction, you can see how that's somehow gathered up in here. Let's read it again. There exists some set x, such that the empty set is in x, and for all y, if y is in x, then the set containing y is also in x. So let's think about what we know about this set x. So we're guaranteed that there's some set x out there, that it contains the empty set, so I know the empty set's in there. Okay, so this thing has to be in there. But what else do I know? I know that anytime you find a set y in x, then the set containing y must also be x. So you know that the empty set is in x. So what else has to be in x? The set containing the empty set. Let me come at this a little bit different way, a way I introduce induction, and then we'll go back to that. I tell you that there's a secret set I have here. My secret set A. I'm only going to tell you two things about this set A. First thing I'm going to tell you about A is that 0 is in A. That's the first thing I tell you about. The second thing I tell you about A is that anytime x is in A, that implies x plus 1 is also in A. If you can ever find a number in A, I'm telling you that that number plus 1 is also in A. So what do you know about the set A? You know it has 0. I gave you that. But you also know that anytime you can find a number in there, that number plus 1 has to also be in there. So since 0 is in A, what else has to be in A? 1. And since 1's in A, what else has to be in A? And then since 2's in A, you know 3's in A. And since 3's in A, you know 4's in A. And since 4's in A, you know 5's in A. Dot, dot, dot.
You're saying that's what Axiom 7 is saying?
Very similar thing. Actually, logically equivalent, but...
Wait, are you saying like the set?
So, we know, so in our example over here, this A here is acting the exact same way as X over here. And 0 here is acting the exact same way as empty set over here. And plussing 1 is the same thing as putting the previous number in a set. So, there's two things you know about this set X. First thing you know about this set X is the empty set is in there. Second thing you know about this set is anytime you can find a set in there, the set containing that set has to also be in there. So you know the empty set's in there, that means the set containing the empty set has to be in there. And you know that the set containing the empty set is in there, well then the set containing the set containing the empty set has to also be in there.
That's 2.
And that's one way to define 2. And then since that's in there, you know that this has to be in there. Dot, dot, dot. And it goes on forever. And this set X has infinite elements.
We couldn't have derived Axiom 6 from Axiom 7.
For the power set, the power set is a set of all possible subsets. What would these be the set of all possible subsets of? Well, forget about numbers for a second.
Yeah, but they're not all sets that exist.
But we're not getting all possible combinations of subsets. We're building very particular types of sets.
You are.
But notice that they also give us pretty different things. This one says, give me a set. This one says, give me a set, and I guarantee you a power set exists. It's a set of all subsets. But notice that this one's always finite. It never gives us an infinite set. Here we were given our first infinite set. So this one's very powerful. It's giving us the fact that some infinite set exists. And now, one way to define the natural numbers is to define 0 to be the empty set, 1 to be the set containing 0, or the set containing the empty set, 2 to be the set containing 1, or the set containing the empty set, etc. 3 is the set containing 2, 4 is the set containing 3, 5 is the set containing 4. And then axiom 7 is logically equivalent to saying the natural numbers exist. It's a very common but kind of dated way of doing this. You do something logically equivalent, more modern. And at first it's going to seem like the modern way is uglier, but you're going to see it gives us some nice properties. So a more modern way. There exists a set that contains the empty set, and for every y it contains, it also contains y union with the set containing y. So rather than y meaning it has a set containing y as well, instead if it has y union with the set containing y. Here's what it says strictly. There exists some set x such that the empty set is in x, and for all y, if y is in x, then y union the set containing y is also in x. So let's start writing out this thing's elements. So first thing I know that's in x is the empty set. Now I know that the empty set union the set containing the empty set has to also be in y, or has to also be in x. What is the empty set union the set containing the empty set? Well, it's everything that's in here and in here. It's just the set containing the empty set. Any set union the empty set is just that set.
I did not know that union element.
Every element is a set. All we have are sets inside of sets inside of sets inside of sets.
Kind of like saying those are the same though.
No, I'm saying this is the same as this, but this and this are very different things. How many elements are in this set? 0. How many are in this set? 1.
Oh, okay. So
Think about it as an empty array and an empty array of an empty array.
okay. I get what you're saying now. So if it was like an empty set union 3, it would be set 3.
Correct.
Actually include that. Okay, gotcha.
Okay, so we know another element in here is the set containing the empty set. But now, if that's our y, we know that y union the set containing y is also in there. So now I know y union the set containing y is also in there. And what does that equal? It's everything in this set union together with everything in this set. So that's the empty set comma the set containing the empty set. Squiggly, sorry. Everyone follow that? And so my second set is the set containing the empty set and the set containing the empty set, all together in one set.
So I have a question. If elements, it seems like in other math classes we don't treat elements as sets. So for example,
in most classes, if you were to write something like this, your teachers would get after you.
Yeah, or you could say like 0 union the positive. You'd have to say the set containing 0.
Well, those are saying those are also saying two very different things. There's a huge difference. Let's finish this and then I'll make sure that's very clear that there's a huge difference in what we're doing. Yeah, we typically don't treat numbers as sets. We do it on a very low level and then we step away from that and we stop doing that because it's very easy to confuse yourself and get in trouble. But let's keep going with this for a sec. Okay, so now I know that this is in X. And so now this set, union with the set containing this set, is in X. Or in other words, take this set and add it into itself. So that would give us the set containing, we're going to have the empty set, the set containing the empty set, and then the set containing the empty set together with the set containing the empty set. Did I get them all? Okay. I don't want to write the next one because it's getting big fast. Okay, so you say, now we define 0 to be the empty set, 1 to be the set containing 0, 2 to be the set containing 1 and 0. Here's 1, here's 0, here's 2. 3 to be the set containing 2, 1, and 0. Sorry, I wrote it in backwards order. Here's 2, here's 1, here's 0, here's 3. So you notice, okay, our definition's getting a lot uglier. Here it seemed a lot more elegant. This is getting kind of messy. Why is this the modern way? Why did we abandon this way and move to this way? There's two reasons we really like this set, two obvious reasons. There could be more than that. One obvious reason we like this set is notice that how many elements are in 0? 0. How many elements are in 1? How many elements are in 2? How many elements are in 3? That's one reason we like it. The cardinality of the set is the number we care about. So that's one nicety of it. There's another nicety. It's real easy for us to define the less than relation. If you think back to arithmetic, less than was the only relation that was given to us in the axioms, right? So we were given plus times, and then we were given less than. So there's two ways that you can do arithmetic. You just start with the axioms of arithmetic, and you go from there. The other way we can do arithmetic is start from set theory, and then construct the axioms, and go from there. And so if you were doing that approach where you had to construct the axioms of set theory, you see how easily getting the less than relation would be very valuable. And so what do we mean by x is less than y? Easy. We mean x is a member of y. And so I know that 2 is less than 3 because 2 is a member of 3. In fact, 0, 1, and 2 are the only natural numbers less than 3 because they're the only numbers in 3. And so yes, it turns out, using this set theoretical notation, that this is a perfectly valid statement. 6 is in 7.
That makes sense.
That would make perfect sense. But you would never see that in a class. And now I was warning you that stuff like this, 0 union 1, is very different from something like the set containing 0 union with the set containing 1.
But in previous classes, we had a notion of 0 union 1.
Right, it's a very...
Because we didn't consider them as sets.
Right. Typically, you don't consider them as sets. If you start out with the axioms of arithmetic and just work from there, it's invalid to consider these things as sets. But if you start with set theory and then construct all these numbers from sets, then it's a perfectly valid way to think about them.
What would that set look like if you were to revert to using the empty set?
I can't, this is what's defined it. You're saying, what would it look like without using its definition? Yeah. So, while the notation is perfectly meaningful with this, it's not that useless. It's like presupposing that you already have this notion of set theory, which how many people do? And so you can already get in trouble. And it's presupposing a certain type of set theory that you used. You use this axiom as opposed to this axiom. So it's assuming a lot.
Well, so you're saying that
about your students.
Hasn't been chosen.
This is there isn't.
They still don't use.
I'm sure that they're all used. I mean, and this is still just one version of set theory that we're doing. We're doing what's called ZFC set theory, which is a type of set theory. There's logically equivalent ways of developing the exact same thing. So that's another thing you gotta watch for. But yes, I would never dock you for writing 6s and 7s. I was like, yeah, that's fine. All right. So we did that. We defined numbers. Just a fun little note. We could go on to build all the other numbers now. Now we have the naturals. So one common way of defining the integers. So like -3, one common way of defining -3 is it's an order pair whose difference gives you -3. So I think they do 2, 5 like this for -3. Because 2 minus 5 is -3. And then when you go to define your rationals, so if I wanted something like 1/3, let's see if I can remember how they do this. I think they do it and they think about it like this. A set of order pairs where each of those are integers. So 1, there's a bunch of different ways that we could represent 1. 3, 2 is one way that we could represent 1. Remember the difference gives us it. And then 3 here could be 6, 3. So here's one way of writing out 1/3. Now there's an infinite number of ways to write 1/3, but there's one way to write out 1/3. And then what about when we get to the real numbers? Turns out the real numbers is the power set on the naturals. Yes, I know. Nothing intuitive about that.
Yeah, that is. That's so cool. Are we ever going to learn why that?
Not in here.
We're just going to say that.
I'm just going to say that and let it bug you so much that you go figure it out.
I don't know why that's the case.
So that's how we would define the reals. And so that gives you a notion of how we could start constructing all these sets of numbers that you know and love so much.
And again, those numbers you just barely wrote down inside of that, those definitions, I could technically just gather them out into empty sets inside of sets.
It's all empty sets inside of sets inside of sets inside of sets.
It's all sets.
Turtle all the way down.
And this is just including, this so far is only numbers and sets. Don't have, can't put any random symbol in there.
We can't put any random symbol in there, but any mathematical notion has a set theoretical definition. Like you might think back to when we did computation theory even. Computation theory, something like a Turing machine, it was this ordered set of Q, that's a set of states. Then you had your alphabet symbols, that was another set. And then you had your tape symbols, dot, dot, dot. It was just this ordered collection of a bunch of different sets. And an ordered collection is just a set. And so it's just a bunch of sets. Every mathematical object just comes down to all these sets.
Okay, and then you were defining like divide, negative, and is there, and my understanding is as you described the set of that representation, the information is never lost, and that's important. And if I was to just see that, I could just say, oh, that is this number, like there a time for two things that essentially represent two different how can I say this? I'm just going to formulate it a bit.
All right. Okay. So we did that. What does it mean for sets to be disjoint? Okay. X and Y are disjoint, provided that their intersection is the empty set. Disjoint means they don't have any elements in common. So if A is equal to the set 1, 2, and B is equal to the set 3, 4, then A intersect B is equal to the empty set. There's nothing in common between those. So these are two disjoint sets. So that's what it means for two sets to be disjoint. Two sets are disjoint provided that their intersection is 0 or their intersection is the empty set or their intersection is the empty set. Same thing. And then a collection of sets, X, is mutually disjoint if for all A in X, for every set in X, X here is going to be a set of sets. So it's going to be like this. So a collection of sets X is mutually disjoint if for every set little a in X, there exists some other set B in X where A is not equal to B. Sorry, I said there exists. For any set A in X and for any other set B in X where A and B are not the same set, their intersection is empty. So take a whole collection of sets. It's mutually disjoint if each set has distinct elements. So if I had some big group of people and I split them all up by last names, so we had all the sets of Timpsons, all the sets of Newtons, all the sets of Hammonds, the set of all Hammonds, Newtons, Timpsons. Those would be mutually disjoint sets. No person shows up in more than one of those sets. If I took everyone who's a Timpson and a Newton in terms of their last name, that's no one. Because you can only be one or the other. That's what we mean by mutually disjoint sets.
What's the symbol for
that? We don't have a symbol for it. We just say this collection of sets is mutually disjoint. And if you want to symbolize it, that's to symbolize it. For any two sets in there, if they're not the same set, their intersection is empty. They don't have anything in common. Okay, really weird one here. Axiom 8. It's called the axiom of choice. That said element. So let X be a set whose elements are non-empty and mutually disjoint. So X here could be like the set of all Timpsons, Hammonds, Newtons, blah, blah, blah. Where that's a set of all Timpsons, right? So this is a set of sets. With me? So let X be a set whose elements are non-empty and mutually disjoint. So none of those are empty. We assume someone's in it. Then there exists some other set Y, which contains little t, we'll say little t, little h, little k, dot, dot, dot. There exists a set Y which contains exactly one element from each of those sets. Now this axiom seems a little bit weird because you might think, why couldn't we already do this? I could just take the Timpsons and pick someone out of there, like me, and put me in and take me as that element. And I could have picked some Hammond, I could have picked some Newton. How is this axiom giving us anything? This axiom gives us something when we don't know what the elements in there are. But we just know that there are elements in there.
So it allows you to like specify.
So yeah, if I had 3 rooms and I knew that there were Timpsons behind door A, Hammonds behind door B, Newtons behind door C, and I listen at the door and I know that there's for sure at least one person in each room. Okay, I'm guaranteed that someone's in there. But I have no clue who's in there. I'm still guaranteed I can create a set by taking one person from each of them. And for those of you with some more advanced math, this is what enables us to create a set of basis elements. If you've ever come across basis elements before. And I think we'll probably use this axiom once in all of topology directly. Very weird one. So it helps in a very particular case. In the case where you have a bunch of sets, but there's no way to identify a particular element in the set. You know that there's something in there, and all it has is this high-level property. But when you look in there and try and distinguish between 2 individual things, there isn't really a way to do it.
If there is a way to know that something is able to specify from the set.
Sometimes we can know something's in a set without knowing what particularly is in the set.
You can still name it.
We know that there's something in there.
Wasn't that the whole part of logic? Law universal specification. You're saying if something's in a set, you can pull something out of it.
Right, you could potentially pull something out of it. But if you had a room full of Timpsons, I told you we have a room full of Timpsons right here, but you didn't know anyone in it, you can't name a particular person in there.
You could assign a name and say it's
Right, but you don't know a particular one. So who did you grab? You don't know. You just know you grabbed someone.
Yeah.
And so you have an arbitrary element.
that's not good enough.
It's not good enough because we don't know what it is.
But if you don't know what it is, how are you supposed to do it?
This helps us do it. We take those we don't know what they are, and we can put them in a set.
I don't really see how that helps, but maybe we'll see that.
It helps in very special cases that don't come up a lot. So I told you that we're in ZFC set theory. There's a notion of ZF theory where you don't include C. C means you included this axiom of choice. Oftentimes people leave out this axiom of choice. No, it's an axiom of choice because it's saying that you can choose one thing from each of these sets. Not you choose whether or not you use the axiom.
Pretty significant name of the axis.
So it turns out there's a lot that you can do without this axiom of choice, but there are places where, okay, we need it. We're going to have to talk about basis elements at one point in this class, so we're going to have to come back to using this.
I'm just not quite sure how it actually
I feel like we've been using there exists some
It's-
element.
It's
in a
not a very intuitive one, and it's the hardest one to see. How does that give us anything useful?
set. It just seems like we've been using that term all the time. That there exists some element in the set. We don't know what it is, but this is the case. We say that all the time. I'm wondering how we've been saying this that whole time.
So when we've been constructing sets, we were always doing it with sets that we knew. Sometimes in an example, we don't bother naming specifically what the set is. But anytime we were constructing a set, it was from sets we precisely knew.
And that's why you were able to describe it. Like, for instance, you probably won't be able to give this equation this any more than you have because we don't know what the sets are. Never know what sets really are.
There's no way of distinguishing the particular. Here's one way that it's often given intuition. Imagine that you have, first off, a bunch of pairs of shoes as a set. Right? So if I went and grabbed a shoe from each one of your pairs of shoes, you had 10 pairs of shoes, I went and grabbed one from each of those, and I showed it to you, you could tell me exactly which elements I grabbed. You could say, you took the left one from the first pair, the right one from the second pair, the left one from the third pair, da-da-da-da-da. Now I replace those with socks, pairs of socks, and you laid them out left, right, left, right, left, right. And I went and took the left sock in the first one, then the right, then the left, right, 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 left. I said, okay, which ones did I take? There's no way for you to tell me, because there's no difference between the left and right sock. All you know is I took one, but you don't know which one. And there's no way for you to distinguish which one, because they're socks, not shoes.
And how would you deal with properties? Like,
This is just given intuition.
You're trying to deal with the fact that it's a left sock or it's a right sock, but you can't tell which one it is. How are you supposed to deal with it? When you pull it out,
How are you supposed to put it in a set?
So all we know is that if we had those sets of socks, and I went and I grabbed up those one from each of those sets and put together a set, that new thing is in fact a set of socks.
You still have no idea. You couldn't derive that before.
No, I could just take a collection of those things and called it a set. In order for me to do that, I would have had to been able to come up with some functional relation mapping from these things so that the right-hand element, it maps to one and only one thing, and then gather up all those right-hand elements, and then I can say, okay, now it's a set. And I couldn't have done that.
Why?
Because I need to map each thing to one and only one thing, but I can't tell the difference between those two socks. How am I going to map them differently?
Okay.
But
That makes sense.
we're getting carried away with an analogy.
No, that helps.
Okay, wonderful. All right. So weirdest one, I think we'll use it once through all of topology, and then that'll pretty much be it.
Are these the axioms of topology? Oh.
Yeah, topology you can just construct right on top of set theory.
Yeah, anything?
You don't need to add anything. I mean, as we go forward, you can add things. So if we want to talk about topology with the real numbers, you got to add axioms on the real numbers. But to talk about just topology in its bare naked sense, you don't need anything. You just it's very low level. You could define a topology just with set theory.
So really it's like a
That's what I'm saying. Set theory, it's a very natural place to start topology. Okay, last one. Every non-empty set X contains at least one element Y such that X intersect Y is the empty set. Intuitively, what this stops us from doing is stuff like this. Let X be the set containing X. These two sets can't be equal. I'm guaranteed that X is never equal to the set containing X. That's what it's given me.
I mean, I see, I hear what you're saying. I'm not seeing how that translates.
So, let's see. Say, is it possible for X to equal the set containing X? Is this possible? Question mark, is this possible? Can I have this equals this? Ever? And the answer is no. Why is the answer no? Because this guarantees me that every non-empty set, here's a non-empty set, contains at least one element, here's the only element it contains, such that when I intersect the whole set with its element, I get the empty set. Imagine that X was equal to the set containing X. So then what would this look like? What would X intersect the X set containing X look like? it would just be X again. If this set was equal to that set, then this intersect, every set intersect itself is just itself. It would be equal to that, which is the same thing as this.
Isn't it because X is actually an element? It doesn't.
If it was ever possible that a set was equal to a set containing itself, then its intersection would always just be itself, and it wouldn't be empty.
Your axiom says that.
It's an axiom that says, don't break the rules like this. You can't ever do this.
There's really quite a few axioms that prevent self-reference.
This is the only one that explicitly does it I know of.
That explicitly does it. The other ones, they have safeguards in place.
They have safeguards in place that say you need to construct from here. Yeah. So, yeah, it helps us with a bunch of our self-reference stuff. Okay, and that's it for set theory. We did it.
Cool. Okay, so I understand that
While you're talking, I'm going to move this.
I understand that there are axioms that are very fundamental and they don't prevent self-reference. And then there's a bunch of axioms that do either prevent self-reference or prevent like 0 should never equal 1 type of thing.
Right.
And it just seems like you could, I don't know, it's like, that's what I meant by certain axioms, I guess, are really compound in the sense that if you're like, well, we don't really want to try to define this, and so we're just going to say it has no definition. We haven't figured out how to define that.
So we can prove that an axiom can't be defined because it's independent from the other axioms. We have a way to prove axioms are independent of each other. How do you do that? You come up with an interpretation where all your, so if I had some axioms, A1, A2, A3, and A4. And A4 here is one of these axioms that you're like, that's just a cop-out. You can't figure out how to define this thing using axioms 1, 2, and 3, and so you're just adding it. Maybe you just need to be more clever somehow. We can prove that it's different if we can come up with an interpretation where this is true, this is true, this is true, and this is false. If that is ever possible to do, then this axiom has to be independent of these. Because if it was somehow dependent upon these things, then it would be impossible for it to be false while all these were true. So if you can do that, then an axiom is independent. And so all our axioms are demonstrated to be independent of each other this way.
I get that axiom is independent. And let's say there's a fifth axiom that is fundamental, and it's not trying to prevent self-reference or something weird, and that it could describe axiom, or now axiom for definition or something. Like, it just seems like there's more to look into, and we just came up with a quick fix.
If you say, so maybe now there's some axiom 5, and now with axiom 5 I could get axiom 4?
That's fundamental and it's not preventing self-reference.
Okay, so say axiom 5 is some new axiom. And you want to know, could I somehow get axiom 4 from it? Check. If it's possible for axiom 5, axiom 1, axiom 2, axiom 3, and axiom 5 to be true, and this to be false, then you cannot get this from this. How do I check, does alpha imply beta? I want to know, does alpha actually imply beta? Or will I have to check beta some different way? If it's ever possible for this to be false and this to be true, or sorry, for this to be true and this to be false, then alpha doesn't imply beta. That's the check. Do I want to know, do these axioms somehow entail this? If it's possible for all of them to be true and this to be false, then they don't entail it. Because if they did, it would have to be true. That's what we do when we prove a theorem. A theorem, we always prove, is entailed by all our axioms. Anytime our axioms are true, our theorem has to be true. If it was possible for it to be false, we wouldn't have proven it. And so we show that they tautologically imply that. They imply it in a way that's always true under every interpretation. And so that's the check.
Okay, I don't fully understand what you're saying, but try to intuitively understand it, or what you're trying to understand. What you're trying to say is that we have proven that all these axioms are fundamental. And there are no axioms that rise or produce that axiom.
You
No
could.
other definition, nothing, no other.
All the axioms are independent of each other. We know that.
Okay, I agree with that.
You could come up with some different axioms that, okay, then these become definitions. Fine.
Yes.
That's fine. So you can sometimes have your axiom, these as your axioms, and from it you define these, or you can have these as your axioms, and from it you define these. And it turns out those are logically equivalent. There's a bunch of different axiomatic ways of setting up Euclidean geometry. But they're all logically equivalent. When it's all said and done, we're proving the exact same theorems.
But what you're saying is that we have proven that we've gotten down the front of these axioms.
I don't know what you mean by gotten down to fundamentals. There isn't some objective notion of this is now the fundamental. I don't know what that means to be fundamental. What we do know is that the axioms are independent of each other. You can come up with logically equivalent axioms and say, why didn't we do it this way? Well, doesn't matter. It's like, do I have a definite, it's kind of like this. Do I say, I kind of showed you when we went over arithmetic. I said, here's one way I like to define subtraction. And then here's a theorem that you can prove from it. But the author used the theorem as a definition of subtraction and then proved my definition as a theorem. It's like, should we have this as a definition and then this as a theorem? Or this is my theorem and this is my definition and this is my theorem? Which way should we do it? It's logically equivalent. So you can get similar notions when it comes to an axiom. Should I have this as my axiom and then define this notion? Or should I start with this notion as my axiom and then define this notion? And so there's a lot of things like that where it's just kind of a matter of preference. You choose one as your axiom and define the other. Just make sure you don't use more axioms than you need. And so if I accidentally add something that's an axiom, I can always check.
I have another question.
Another question about what?
Axiom 9.
About axiom 9,
Yeah.
okay?
Say it contains at least one element y, such that x intersect y is the set.
Right.
Does that mean that every element in the set satisfies that, or just that at least?
No, there's just a particular one. So in the example here, I gave us a set with exactly one element in there, so it was the only one we could check against.
But in another set, that might not be the case. You could have x intersect y where it is equal to something, as long as at least one of the elements satisfies that.
So you might be tempted to say, okay, maybe I can define x to equal the set containing x comma y, right?
Yeah.
But then from this notion of a set, I could define into existence what's the best way to say this? I can start constructing that bad set again.
Yeah.
And so you're going to have to be clever with how you work with it. But if you allow things that you intuitively know shouldn't be able to happen, you're going to be able to ultimately construct a bad set from those bad sets that ultimately lead to contradiction. Because
x inside the set there, x fills that requirement.
right, I'd have to get clever with it, but somehow I'm going to be able to start taking that set, treating it, okay, if this is a set, then I can intersect it with this other thing that I know is a set, and then I can keep working with it till I get what's obviously a bad set. And so allowing it to exist enables me to come up with a set that will end up breaking this.
You could just subtract the set containing y, something from that, and then you end up with a bad set? Is that what you're saying?
No, in that case it wouldn't work because x is a set x containing y. If I subtract away y, who's to say I still have x? So it doesn't quite give it to me, but I don't know. You'd have to be clever with the problem. But there would be a way to mess with it. So it's if you introduce sets that intuitively you know you shouldn't be able to do this, then it's the one that enables you to work with it to show explicitly you can't do it.
I just contacting the Axiom enforces that.
I wish I had a good example off the top of my head on how to do it, but I don't. All right, so we'll end it with set theory there, and from here on out, we're pretty much going to use naive set theory. And so we're going to use set builder notation. We'll use both set builder notations. I'll sometimes say the set of all x such that, and then I'll also say the set of all x like in the real numbers such that. And we'll see both those. And we won't exclude ourselves from using this. Okay, so now we're starting the actual textbook. So chapter 0, introduction. The book is called An Introduction to Topology, Pure and Applied. There's the ISBN number in case you care. I'll post it on the Facebook page, the actual book. So you have access to the book. But if you want to go buy a hard copy or whatever, there it is. Okay, I already gave you some high-level notion for what exactly topology is. Let me say this for a second. Topology is a little bit of an equivocal term because there's a class called topology, but in this class we're also going to construct an actual structure called a topology. It's like if instead of computation theory we would have called that class Turing machines, and then in the class we also studied an actual object called a Turing machine, or we do this in algebra. You have a notion of what algebra is. It turns out there's also a structure called an algebra. So we're going to define an actual structure called a topology. It's going to be a set of things, but it's also going to be a name of the class. So don't let that confuse you. And I gave you intuition already for what topology is. It's often called, people sometimes loosely call it less structured geometry or rubber sheet geometry. And I told you that in topology, what we care about is preserving proximity. When they first started developing topology, the first name they applied to it was the geometry of just position. So topologies are about preserving proximity. So you remember going back to triangles, every field of mathematics has its is the same property. In geometry, the is the same is congruent. What did it mean for one triangle to be congruent to another triangle? It meant all their sides were the exact same length. That side was the same big as that side. This side was the same big as this side. And all their angles had the same measure. That angle had the same measure as that. That angle had the same measure as that. That angle had the same measure as that. So the sameness relation in geometry captures a lot of structure. In topology, our sameness relation is going to be, all the points have the same proximity to each other before and after. So in topology, a circle is topologically equivalent to this thing. The way I like to think about it is a rubber band. Imagine I had a rubber band. And you think about atoms as points. And so I think about this atom, and it is connected to this atom. Those are the two atoms touching. They're the ones that are close to each other. That's what I mean by close in this analogy. Two atoms actually touching each other. Now I take that rubber band, I distort it and stretch it in a way that doesn't deform it, doesn't break it, anything like that. So now those two atoms are right here and right here. Any two atoms that were next to each other before I stretched and deformed that, or stretched out that rubber band and twisted it, are still next to each other. But the distance between this point and this point is now drastically different. So in topology, these two are the same. On the other hand, if I break the rubber band, and so I tried to stretch the rubber band, and so now we had this thing, now it's not topologically the same. Because before, this atom and this atom were right next to each other, but now I broke them. And this atom's right here, this atom ended up here, this atom ended up over here. They're no longer right next to each other. So I didn't preserve proximity, so these would not be the same in topology.
Atoms have the same.
It's just an analogy.
I know. So it doesn't matter the distance between two nodes, essentially. Like, as far as the distance between the two things connected.
The 2 points are still touching. That's what I'm going to say. Notice now that those two atoms were touching, and over here they're definitely not touching. Similarly, here's something else that would have preserved the proximity structure. Maybe I take these two ends together, and I apply a lot of heat, and I kind of weld the rubber band together there. And so now the rubber band looks like this, with this welded point in the middle. Those 2 points weren't next to each other. And now I melted the rubber band together, bringing those 2 points together. Now they are touching. Those are no longer topologically equivalent. So those are not the same. The typical example of the weirdness of topology is in topology, a coffee mug. Let's see, I'm going to be in trouble with my art here. Coffee mug is topologically equivalent to a donut. Those are the same topologically speaking. And how might I get that coffee mug transformed into that donut? So imagine it's like this rubber stuff. I can kind of shift the mass around to it. I just can't. Basically, the two rules are no breaking. So I can't snap anything in half. I can't take the handle and break it. And similarly, no hooking things together. I can just kind of shift stuff around. And so how would I get a coffee mug in the shape of the donut? Well, first I kind of flatten it all out, right? Flatten out the coffee mug. And then we got this kind of plate thing with a loop there, and then just redistribute the plate thing around the loop, shifting the mass around. I could keep working with it and get it in the shape of a donut. No, this coffee mug is not a hole in a topological sense, right? It's just a wave down and back up. I can squish the sides down, and there's no hole there. I didn't fill in the hole when I did that. Right? I could keep squishing down the sides smaller and smaller and smaller. And the book tries to give some demonstration showing the coffee mug in a bunch of different states of squished. Gradually trying to give you this intuition for turning it into a donut.
So the hole in the donut is the loop.
Yes, that handle ends up the hole in the donut. And so the number of holes it had topologically speaking is the same before and after. Just like over here with our rubber band. The number of holes has to be the same before and after or we cheated. Over here, we turned one hole into two holes. We cheated somehow. Can't do that. So, high-level intuition for what topologies are capturing. Proximity, and that's it. And it turns out, I know that you said shift mass around, and that seems kind of like a weird thing to do. But remember, with the number line, shifting mass around is kind of like just scaling up or scaling down, which doesn't really change anything. Just makes it bigger or smaller. So taking something and making it smaller, it'd still be topologically equivalent. And stretching out, making it bigger, still topologically equivalent. So we just scale down that part of the coffee mug and scale up the handle over here. That's how you redistribute mass. Okay, anyways, that's very high level for what topology is and the intuition that they give you. Now, topology is such a low level class, and we're dealing with such low-level concepts, it's so hard to get intuition for this stuff. It's not like when you're doing arithmetic, every kid has great intuition for arithmetic. What should 5 plus 3 be? 8. Every little kid knows that. The intuition's great. Even with calculus, you have a ton of intuition from the real world, calculus with physics. Topology is a very low-level class, and so getting intuition is a pain. And so there's something that we're going to do over and over again in this class. So we're going to assume basically all of arithmetic, all the axioms on arithmetic, the completeness axiom, all that stuff. But we're assuming that for the sake of examples. So I can give you examples from all these things to help give you intuition for what topology is. So we're going to be rigorously developing topology. And then our examples, we're going to jump and say, okay, I assume that you know something like addition without ever giving a proper, completely straight, set theoretical notion of definition or of addition. And we're going to be using stuff like that for the sake of these examples, for the sake of the intuition. Because I'm going to commonly have to try to give you intuition and then go down to the rigorous proof. Because as a general rule of thumb, you don't try proving something in math until it almost feels obvious. And so trying to make it almost feel obvious is going to be the big challenge here. Because of how low level it is. So that's a sign up. All right. Common sense. Common sense we all know and love. What's that? The empty set. The set containing nothing. What's that? Natural numbers. These are the numbers. 0, 1, 2, 3, 4, 5. I always start the natural numbers with 0. Some authors start the natural numbers with 1. We don't like those authors. We hate them very much. The natural numbers start with 0. That's what this axiom gives us, the natural numbers. We don't want to get rid of the empty set. What a stupid thing to do. I followed what the author did.
People that don't acknowledge zero in the natural numbers, do they have a set of nest numbers? Does that include it? What symbol do they use?
They don't have a symbol, but they call it the counting numbers. No, because that would be, whole numbers would include integers.
No, they have, well, at least in my college algebra textbook, it was natural numbers are from 1 on and the whole numbers are 0. Which didn't make a lot of sense.
They said whole? You sure they didn't say counting?
No,
That sounds right.
I'm guessing they said counting. That would be a super dumb thing for author to say. Okay, anyways. The empty set. The naturals, they start with 0. Z. Integers. Let's see integers. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, along with -1, -2, -3, -4. So 0, all the positive whole numbers, and all the negative whole numbers. Z plus, with the plus up there. That means just the positive integers. So this is how we represent 1, 2, 3, 4, 5, 6, 7, 8, 9, if you don't want the 0. Includes the 0? Doesn't include the 0. Just the positive integers.
So
0 is not a positive number.
0 is an integer. Okay.
0 is an integer.
Okay.
It's not a positive integer.
Just take me a second.
And z with the negative sign there, that's the negative integers. So if we want to talk about negative integers, there we go. We want to talk about the positive integers, there we go. We want to talk about the naturals, there we go. All the integers, there we go. And then q. What's q used for? The rationals. What are the rationals? Intuitively? It's a set of all fractions. All fractions are rational. So 3/4. This is not an integer. It's not a whole number. It is a rational. Any number I can write as a quotient of 2 integers is a rational. -1/99. Okay, there's another rational. So those are the rational numbers. Any number that can be written as a quotient of 2 integers. And then finally, there's the reals. Oh, sorry, we're right here. And then same thing with the rationals. I can talk about if I put a plus up there, that means all the positive rationals. And if I put just a minus up there, that means all the negative rationals. Make sense? And then finally, we have the reals, just that are without those things up there. What are the real numbers? If you don't know what complex numbers are, what you think of as a number is a real number. Any notion you have of a number, it's a real number. So, for example, the square root of 2 is something that's not rational. You can't write the square root of 2 as a fraction. There's no way to do it. Pi is another example, but it's a real number. Square root of 2 is still a real number. We just can't write it as a fraction of 2 numbers. Same with pi. It's a real number. We can't write it as a fraction of 2 numbers, of 2 integers. And then, if you know what the complex numbers are, you obviously already know what the real numbers are, so I don't need to explain it to you.
Are we giving any examples?
We may touch on the complex numbers a couple times. I don't remember if we ever do in the class in a couple examples. If we ever touch on them, we'll explain it as needed. But
complex numbers are the simple I.
all right, yeah, complex numbers. What's a complex number? It's an ordered pair of real numbers, a, comma, b, I, where a is a real number and b is a real number, and I is the square root of -1. That's a complex number. Okay, you can go ahead and forget that.
I had a lot of people try to explain it to me, they don't understand. But that's okay.
It's just an ordered pair of real numbers, where the right one you pair with I. Just 2 real numbers. Or one's paired with I. Okay, but if we ever come across complex numbers, we'll give it a much better explanation. But for now, don't need them. Okay, now, interval notation. Hate that we have to do this, but we have to do this. Because we use this notation so stupid much it hurts. Because of how much we use it for different things. So parentheses are used way too much in math, right? We use parentheses for like 3 plus 7 plus 9. If I want some precedence, I put parentheses like that. Now we also use parentheses for an ordered pair. Like if I were talking about the point on the plane where you go 3 units to the right and 4 units up, I use 3, 4 like that. Now we use these parentheses for something called interval notation. If I want a way of representing all the real numbers between the number 1 and 5, I also represent that this way, 1, 5, for all the numbers between 1 and 5, as an interval. And it will often be obvious from context that I meant it as an interval, but it's still annoying that we use that notation, and you just have to get used to it. Yes, so here's our interval notation. Understood as an interval. So we're not talking about an ordered pair. We're not talking about a point on the plane. We're talking about an interval. When we see A and B as an interval, if I ever say the interval AB, what do I mean? I mean the set of all real numbers, all x in R, such that x is between A and B. If we were looking on the real number line, and A was our number 1, and B was our number 3, we're talking about all the points between 1 and 3, all the real numbers between 1 and 3. So not quite including 1, so we don't include 1, but all the way over to not quite including 3. If you remember back to like your old algebra days, you often had to draw little pictures like that. And you would use an open parenthesis right there to say, and we don't include 1, and we don't include 3. So open parenthesis, A comma B, open parenthesis again. That's a set of all x where x is between A and B. X is greater than A and x is less than B. Now, if we replace those parentheses with these brackets, these square brackets, then that means x is greater than or equal to A and less than or equal to B. So in this case, x could actually be A. If we were talking about the closed interval 1, 3, this contains the number 1 and this contains the number 3. So these points are actually included. Oh, oops, when you drew it on the number line, that's not what you did. When you didn't want to include them, you did an open circle there to say, and we don't include those, but all the points up to it. And when you did want to include them, then you fill it in at those points, and that means do include them. And that's the pictures you drew way back when.
For arrows.
Arrows are for the cases we're coming to. Okay, now we have a set like this. We have a square bracket on A, but an open bracket on B. That's a set of all x that are greater than or equal to A, but less than B. So if it's a square bracket, it just means include it. If it's an open bracket, it means all the way up to, but not including. Similarly, open bracket A, square bracket B, that means all the x's that are greater than A and less than or equal to B. All right, over here, what about A to infinity? What does that mean? That means all the numbers greater than A and less than infinity. Which numbers are those? Those are just all the numbers greater than A. So that's the set of all x in R where x is greater than A. If we had a closed bracket here to infinity, closed bracket A to infinity, that's a set of all x in R where A is less than or equal to, or where x is greater than or equal to A. A is less than or equal to x, same thing. All right, negative infinity to B, where we don't use a closed bracket, that's all x less than B. Negative infinity to B closed bracket, that's all x less than or equal to B. And then finally, negative infinity to infinity, that's all the real numbers. One more side note, if it's a closed interval like this, from A to A, that only has the point A in there. So all the x greater than or equal to A and less than or equal to A is just A. A is the only thing both greater than or equal to A and less than or equal to A. So that's all our different interval notation. Okay, which of these do we call open intervals? We call that open, and that open, and that open. Which ones do we call closed? We call this closed, this closed, this closed.
All those closed.
Yep. And then we call this one bounded and closed. And from topology, you will get perfect intuition for why we call those things closed and why we call those things open. But I just might accidentally say, let's look at the open set AB. Or I might accidentally say, let's look at the closed set AB. And if you're ever confused as I write it out, you can always ask why I'm saying that. So those are what those are. Okay. So that introduced that interval notation. I think we can end it there, and we'll start with the first definition in the book next time. Any questions on what we covered? Questions about the class in general? Books online?
I do have one about your X class line notation, but we don't have to do that in the video.
Okay. Turn this
The
up.
link that you have for your logic was for
Did I post a link?
on Facebook page.
Okay. I can send it to you.